Okay, we are on Lewis structures for covalent compounds, and covalent compounds are made of nonmetals. When we draw the Lewis structures for them, they're going to be a little bit different than those for ionic compounds. So what we're going to be doing here is sharing electrons. And if you take a look at water as an example, when you're drawing the Lewis structure for a covalent or molecular compound, what you want to do is make it look symmetrical if you can. So I'm going to put the oxygen in the middle. I'm going to put the hydrogens on either side. And then what you want to do is connect the symbols with lines. These lines are known as a single bond. A single bond has two valence electrons, and they are shared between the two atoms. Okay? So sometimes they call this a pair of electrons. Sometimes they call this a bonding pair of electrons. And what we have to do is figure out how many valence electrons we have to work with total. Hydrogen is in group 1A. Oxygen is in group 6A. So if you don't have your periodic table out already, you want to get that out. And the number that's in front of the A indicates how many valence electrons each one of them have. So if I have two hydrogens in 1A, I have two electrons to work with there, plus I have an oxygen in 6A, so that means I have 6 electrons from oxygen. 6 plus 2 is 8 valence electrons total. I used 2 here in this single bond and 2 here in this single bond. So I used a total of 4 when I drew in my single bonds. 8 minus 4 leaves me with 4 electrons remain. What you do with the remaining electrons is you put them on in pairs. You never separate them. They're always in pairs. You put them on in pairs here on the oxygen. You don't put them where you've drawn a single bond. And hydrogen actually never wants to have any lone pairs of electrons on it. It only wants to have a single bond coming off of it at one time. It's kind of an exception, not kind of, it is an exception to the Octet rule. So oxygen is now surrounded by 8 electrons, and oxygen is happy, and that's the proper Lewis structure for water, okay? Now, we would call these electrons here a non-bonding pair of electrons, and we would call this a bonding pair of electrons. This non-bonding pair of electrons may also be known as a lone pair of electrons. Okay, so I have 2 lone pairs on water and I have 2 bonding pairs. Now, that's a single bond between oxygen and hydrogen. In terms of the bond length, single bonds are the longest bonds. Okay? Now, let's take a look at another substance. Let's look at chlorine. Remember I told you that if you're drawing a Lewis structure, you want to make it look symmetrical. You want to connect it with a line that stands for a single bond or 2 valence electrons. On the periodic table, chlorine is in 7A. So 2 times 7 is going to give me 14 valence electrons to work with total. I used 2 when I drew in that bond, so I have 12 left. You put the remaining electrons on the chlorines in pairs. So you have 2, 4, 6, 8, 10, 12. You don't put them here where this bond is. Now I've got the left chlorine surrounded by 8, the right chlorine surrounded by 8, and that's the proper Lewis structure. So I have a bonding pair, 1, and then I've got 1, 2, 3, 4, 5, 6 non-bonding pairs or 6 lone pairs of electrons. Okay, now in terms of O2, let's do O2 as the next example. I want to put them next to each other, connect them with a line, which is a single bond. Oxygen is in 6A, so I have a total of 12 valence electrons to work with. I drew in 2 with that bond, so I have 10 electrons left. So 2, 4, 6, 8, 10. I didn't have enough to put 8 electrons on everything. When you run out of electrons, and you need to share a pair of electrons here to create a double bond, so that way you can go ahead and make both of them happy. So here, this oxygen is surrounded by 2, 4, 6, 8. This oxygen is surrounded by 2, 4, 6, 8. They're both happy, and that's the proper Lewis structure for O2. So you don't share a pair in the middle and create a double bond unless you run out of electrons to create 8 on each. Over here, I didn't run out, but here I did, and that's why I had to make a double bond. Double bonds, in terms of their length, are shorter than single bonds. Now, let's take a look at N2. N2 will look symmetrical if I put them next to each other. Nitrogen is in group 5A. So 2 times 5 is going to go ahead and give me 10 valence electrons. When you draw in a line, you use 2 electrons. I have 8 electrons left. I'm going to put the remaining 8 electrons on the nitrogens in pairs. 2, 4, 6, 8. I ran out. I don't have enough to make an octet on each one. So that means you need to take a pair and share them in the middle. I'm going to take this pair. I'm going to put them here. When I do that, it makes the oxygen on the right happy because now it's surrounded by 8. But this oxygen on the left is only surrounded by 6. So you need to take another pair off of this nitrogen, put them here to create a triple bond, and now that's the proper Lewis structure for N2. Triple bonds are the shortest in length, okay? So all of these steps that I've been following are outlined on the next page. One thing that I need you to note is that there are 3 elements that are exceptions to the octet rule. You've already seen one of them. It's hydrogen. Hydrogen is in group 1A, and it has 1 valence electron. So it needs to share that with something else to create a bond. So if you have something come across and bring its valence electron over, now we're going to have a single bond coming off. So this is why hydrogen will form a single bond, okay? And that's it. It will have nothing else. The other element that you need to watch out for is boron. Boron is only going to want 3 single bonds coming off of it at any given moment in time. And the reason for that is because it is in group 3A. It has 3 valence electrons. It needs to share them with something else so that if something else brings an electron to share, it will form those bonds with it, okay? The last one is beryllium. Beryllium is in group 2A. Beryllium has 2 valence electrons, so it needs to share 2 electrons with something else. Therefore, beryllium will only form 2 single bonds coming off of it at any given moment in time.